Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 56 on Approximation and Error.
We've seen the big picture of how Taylor series and polynomial approximations to functions work. In this lesson, we're going to change focus and detail exactly what happens when we perform approximations.
By now, you know that the sum of 1 over n squared converges, since it is a p-series with p equal to 2. But to what does it converge? We've claimed in the past that this converges to pi squared over 6. That is a deep result. We can't get that easily, so let's approximate. The true value of pi squared over 6 is, in decimal form, 1.6449, etc. How many terms would we have to sum up in this series to get within a certain amount of that true value? Well, let's fire up the computer and see what happens if we add up, let's say, the first 10 terms. Then we get an answer that is, well, it's within a neighborhood. It's not exactly really close. So let's add up the first 20 terms and see how close we get. Now we're doing a fair bit better. If we take a little bit more time and effort, compute the first 100 terms, then it seems as though we're definitely within 1% of the true answer. And if we added up the first 1,000 terms, well, now we're getting something that is really fairly close to pi squared over 6. But how close? Well, in general, you're never going to be able to get to the truth. The true answer involves a limit, and that just takes a lot of work. In general, what you can do is come up with an approximation, let's say by summing up terms up to and including a sub capital N. Now, what's left over is the error that will denote E sub capital N. You're not going to be able to compute that error exactly, since then you would know the truth, but you can control or bound that error. Let's see how that works in the context of an alternating series. Let's consider a series that satisfies the criteria of the alternating series test. That is, the sum of -1 to the n, a sub n, where the a sub n's are positive, decreasing, and limiting to 0. Then remember how this convergence happens. As you take the partial sums, you're always jumping over the true answer to the right and then back to the left because of the alternating nature. Then, in this case, it's easy to get an upper bound on the error, E sub n, in absolute value. It is precisely a sub n plus 1, the next term in this series, because you're always overshooting. When you have an alternating series, this result is simple and useful. Let's consider the approximation of 1 over square root of e, with the goal of getting within 1/1000th. Well, if we use our familiar expansion for e to the x, where x equals -1/2, then we see this is really an alternating series, with the a sub n term being equal to 1 over n factorial times 2 to the n. Now, if our goal is to add up a finite number of these terms and get the error less than 1/1000th, then the alternating series bound says that we need to find a capital N so that a sub capital N plus 1 is less than 1/1000th. Well, what is a sub capital N plus 1? It is capital N plus 1 quantity factorial times 2 to the capital N plus 1. Getting that less than 1/1000th is not so hard. That's going to work whenever n plus 1 factorial times 2 to the n plus 1 is greater than 1,000. That's true whenever n is bigger than or equal to 4. So it doesn't take many terms to approximate 1 over square root of e. But let's consider what it would take to approximate log of 2 using the alternating harmonic series. In this case, a sub n is 1 over n. In order to get the error less than 1/1000th, what do we need? Well, again, by the alternating series bound, we need a sub capital N plus 1 less than 1/1000th. That's the same thing as saying n is greater than or equal to 1,000. And that is a lot of terms to get within the same error amount as we used for an exponential. What happens if you don't have an alternating series? Well, you need a different error bound. There is one associated to the integral test. Let's say that you have continued your series a sub n to a function a of x and have shown convergence by means of integrating this function. Then one can see that the tail, the e sub n term, has a natural lower bound in terms of the integral of a of x. Specifically, if one integrates as x goes from n plus 1 to infinity, then that is a strict lower bound for e sub n. Now that's not optimal. We tend to want an upper bound for the error. But note what we can do if we slide everything over by 1 unit. Then the appropriate upper bound for the error is the integral of a of x dx as x goes from n to infinity. This is remarkable in that we get a bound in both directions. With this in mind, let's see what it would take to get close to pi squared over 6 when we sum up terms of the form 1 over n squared. Now we know the value of pi squared over 6, and let's say that we want to get within 1/1000th. Well, we know that this p-series converges by the integral test, using a continuous function, a of x, equals 1 over x squared. By the integral test bound, e sub capital N is less than the integral from capital N to infinity of this a sub x. We've done the integral of 1 over x squared enough times so that you'll believe me when I say that this integral comes to 1 over capital N. Now, if we want that to be less than 1/1000th, that's really saying that n has to be larger than 1,000. And if you'll recall when we did some of our computations, that is exactly what we saw when we summed up the first 1,000 terms. The integral test gives very precise bounds. If you don't have an integral test and you don't have an alternating series, what can you do? Well, there's one last error bound that involves only Taylor expansion, but we're going to pay for that generality in terms of complexity, for the following result is deep and difficult to grasp. For that reason, we'll keep it simple by looking at what happens at f of x for x close to 0. Assume that f is smooth, then Taylor expand f about x equals 0, keeping only terms up to and including order n. Now, of course, f is not equal to this Taylor polynomial. It's just an approximation, so there's some error. But here, the error term, e sub n, is a function of x and not a constant. So what can we say about that error function? Well, the first thing that we can say is that e sub n of x is in big O of x to the n plus 1. That's not too surprising. Everything else is higher order terms. On the other hand, this is kind of a weak result in that in big O, you're only finding out what happens up to a constant, and in the limit as x goes to 0. What we'd really like is a more explicit bound that we can use to get numerical results. Well, there is a strong form of this theorem that says that the error is bounded in absolute value by some constant, c, times x to the n plus 1 over n plus 1 factorial, where this constant c serves as an upper bound to the n plus first derivative of f at all values of t between 0 and x inclusive. This is a much stronger version of the error bound and tells you that it's really the n plus first term in the Taylor expansion that is giving you control over the error. In fact, if you want to get really strong, we can replace that constant big C by exactly the n plus first derivative of f at some t that is between 0 and x. And this is a very remarkable result in that you're not bounding the error. You're saying exactly what the error equals as a function of x. What I'm not telling you is what t you have to choose in order to evaluate that n plus first derivative. Now, I'll let you work out what this would be if you replace 0 with a. Let's see how this bound works in an example. Let's approximate the square root of e within 10 to the negative 10, using the familiar expansion for e to the x and evaluating at x equals 1/2. Then what do we get? We have some e sub n, where, by the Taylor theorem, e sub n is less than some constant c over n plus 1 factorial times x to the n plus 1, in this case, x equals 1/2. And c is some constant that bounds the n plus first derivative of e to the x for all values of x between 0 and 1/2. Now, fortunately, derivatives of e to the x are easy to compute. That's just e to the x. So what is a good upper bound for e to the x? Well, since e to the x is increasing, then a good upper bound would be the right-hand endpoint, e to the 1/2. Well, that number is maybe not so easy to work with. So let's just say 2, because I know that 2 is a reasonable upper bound for e to the 1/2. Therefore, we get that e sub n is less than 1 over n plus 1 factorial times 2 to the n. That's maybe not the best bound we could come up with, but it will get the job done, because if we tally up n plus 1 factorial times 2 to the n for various values of n, we see, without too much effort, that having n bigger than or equal to 10 will work. Well, that went so well. Let's do it again, this time to estimate arcsine of 1/10 within 10 to the negative 10. Now, I won't go through the details of the Taylor expansion for arcsine of x. The terms are a little bit complicated, but not too bad if you assume that they're given. What matters is the Taylor error bound, that e sub n is less than a constant c over n plus 1 factorial times x to the n plus 1, where x equals 1/10. Now, this constant c is the critical piece of information. It's an upper bound for the n plus first derivative of arcsine of x for all x between 0 and 1/10. Now, who remembers the formula for the n plus first derivative of arcsine of x? Anybody? I don't remember it either, and this is the difficult part of using the Taylor bound. You don't necessarily know a good bound for the n plus first derivative. How are we going to solve this? Well, if the Taylor theorem is not going to work, and it's not an alternating series, and I don't think I want to integrate this function, then what do we do? Well, we're just going to have to think. But if we think, well, this is not so bad. Look at the terms in this series. We have 1/10 and then something times 1/10 cubed, plus something times 1/10 to the 5th, etc. It seems as though every step where we go from n to n plus 2, we're picking up an extra 1/10 squared. Okay, so that's 1 over 100. But if we look at the coefficients, the 2n plus 1, and the product of odds over the products of evens, then we're picking up another factor of 10 in the denominator. And I claim that an plus 2, the next term in the series, is less than the previous term, a sub n, divided by 1,000. What this means, really, is that you're picking up 3 decimal places of accuracy with each subsequent term. And that means that if we want to get within 10 to the negative 10th, it's going to suffice to choose n bigger than or equal to 7. So the first 4 terms that we have represented on this slide suffice to approximate arcsine of 1/10 within 10 to the negative 10. Never forget to think, even if a Taylor bound doesn't work. In general, bounding errors is just hard. There's no getting around it. If you're fortunate enough to have an alternating series, then it's not so bad. If you've got something that works with an integral test, you're great. If not, you're either going to have to resort to the Taylor theorem or use your head.
That brings to a close all of the main topics of this course. We're not quite done, though. We still have a few things to say to wrap up this chapter, this course, to give you the big picture and to point ahead to some of the broader ideas you may encounter in calculus and in the world of mathematics.